But you did? So biggest problem with number one, if you struggled to find the integral there, what do we have? 4 over x cubed. I would have made this 4x to the negative 3 so that I could go in and add 1 to the exponent and so on. The only exception to this would be if you had like 1 over x, right? What's the antiderivative of 1 over x? Natural log. I put the plus c there. We haven't really gotten to indefinite integrals yet, but because there are not values. But that goes 1.944 on the integral there. Everybody's okay? The antiderivative, of course, was negative 2x to negative 2, and then that was evaluated from 6 to 1, or from 1 to 6. Everybody good? How about number 2? I know y'all need number 2.
I did trap rule.
Why would you do trap rule?
It was just the only thing that popped in my mind. Yeah.
But if you did trap rule, this is cosecant squared x. I'm going from pi over 6.
Even when I did trap rule, I still.
But I think you all lost sight of what it was you were finding.
I still got the answer right though.
Miss McGee, what?
I still got the answer right.
Did you?
Oh yeah, that's a really big test skills.
Oh my gosh.
Yes.
The dashed lines were even on here for you. So if you did, a lot of you wrote this. And that's actually not the blue shaded area, right? If I find that integral, that is this area. It's from the curve to the x-axis, right? So you would need the area of the rectangle minus the area here. Does that make sense? So I would need the area of the rectangle is pretty easy, right? This from here to here, and a lot of you saw that. That length was 5 pi over 6 minus pi over 6 would be 4 pi over 6, which would be 2 pi over 3. And the height is 4, so I've got 4 times 2 pi over 3 minus the integral. And then y'all did some crazy, crazy stuff trying to find the integral there. Oh my goodness. This ends up being 8 pi over 3. So at the very least, if you realized you had to do, even if you couldn't remember that the antiderivative of cosecant squared, if you realized that it was the rectangle minus the integral of the cosecant squared, then if you look at the answer choices, there's only one that's 8 pi over 3 minus something. Good hint there. It was C.
What'd you get? How many did you take off?
2 root 3. What is the antiderivative of cosecant squared x? Nobody knows? It's negative cotangent. It's negative cotangent. So this is, we do. And what I should have done while I was gone was left you practice on that kind of stuff. And I'm sorry. Y'all, I didn't have a lot of time. I was just trying to, on the fly, find it. And then, yes, this became a unit circle problem. So I got 8 pi over 3 minus. This was probably one of the most difficult on here, I thought. And I've got negative cotangent. I'm going to do 5 pi over 6 minus negative cotangent of pi over 6. You think that would help you?
Yeah,
Okay.
yeah, I do, actually. I really do.
Okay. I know, I'm really sorry about the AP classroom. Clearly, y'all like the Khan Academy better
I
than
like
me.
the AP classroom where it's like, that woman from Florence, I like her.
Okay, well, for the review that we'll watch those videos, and we'll watch all those videos, that's Mark and Verge, and they're both really, really, really great. And they're both AP readers that go through. But we'll do that for review whenever we get there. They work through problems like order on the AP exam. All right. Cotangent is, of course, the flip of tangent. So now I need to know what is the tangent at 5 pi over 6. It's the tangent at 5 pi over 6 is square root of 3 over 3. It's actually negative because I'm over in that second quadrant, right? So if I flip that over, I have 3 over the square root of 3 minus, and then again at pi over 6, and I'm going to flip it. So again, that's just a straight up unit circle question. What do you mean without the value? Well, for my quiz, yeah, you would have gotten points off. But I'd have given you some points. I gave you 2 points if you circled the right answer. It didn't even have work. Yeah. So there you go, 2 root 3 there. 3 was a strictly calculator question. Well, but if your calculator wasn't in radians, you would have gotten D. It's C. Everybody uses my calculator. Always check, though. Check and make sure. Always radians unless otherwise indicated. Always. If it's degrees, it will indicate degrees, yeah. Radians are the acceptable assumed. Hit mode. No, Dylan, I wouldn't do such a thing. Was Dylan the only one that did that? You did it too? I might go back and look at that one.
I do remember that I was looking at it and I like, my answer that I got on my calculator wasn't 0.361. It was like really close to it. It wasn't that. But I mean, I knew I was putting it in right, so I had no clue how to like get anything out. I didn't think about the rating.
But don't let that happen again. Don't do that on the exam. Make sure you're in the rating. Okay. Number 4. Y'all have already asked me about that one. Okay. Make sure you chain rule that. The one we did in class was an x squared, so we multiplied by 2x on the end. This one was negative x, so it was -1 for chain. I didn't take off all your points. If you got A for that one, I think I only took 4 off instead of 7.
I didn't want to put A because the signs were wrong.
The signs were wrong because you didn't multiply by -1. You didn't chain rule that negative x.
I know.
Yeah. Now, this, and a lot of you got confused about when we use that fundamental theorem part 1 and when we don't. This asked us, if this is y, it asked us to find dy dx. So to find the derivative with respect to y. And since I'm doing that, and these are like opposites, right, they cancel out. So I've got 5, I do negative x squared minus 6. I plug in exactly the x the way it is, right? But then I have to multiply by -1 because of that chain rule. So it's the chain of this. And so I end up with, this is 5x squared plus 6x minus 1, and I'm going to change all the signs. It was E. I'm sorry. Hold on to these, though. Keep these because they're good questions. I try to make sure that the multiple choice questions are old AP questions or things like that. They don't always release those, but I have a bank of them. Number 5 is trapezoid rule. And I told you, yes, you could use your calculator to check, but make sure you show the setup. This one was a little bit hard to show the setup on. Let's see, from 2 to 8 up to x cubed x. I think everybody got this one. Anybody need me to work that one? Y'all good? I set up an XY chart. That's what I always do as a T-chart to see what I need to do. I know my intervals. This wasn't the one I was thinking about. If n is 3, 8 minus 2 over 3 tells me that I'm going by units of 2, and I just do. I do that. I find it easier. 2, 4. You have to think about the shapes, though. Yeah. Right. It trips me up a little bit, too. In fact, on my work, whenever I did it here, I went 1, 2, 3. So I could see that it was, yeah. The answer, yes, it is Simpsons. But we didn't, so I took Trap or Simpsons. If you put Simpsons, I gave you 2 extra points. Just because I had mentioned in class that Simpsons was a more accurate estimation. And so if you heard that and put that, I gave you 2 bonus points, but I didn't penalize you for not putting it. How'd you know Simpsons? Did you use the calculator program? That was smart. That you knew the exact area. That was smart, Allison. That was smart. All right. I don't know, but it's just, that's why we say diff. It's literally just short. Diff differential equation. You thought I said what? No. All right. What's a differential equation? Good answer. Good answer. So we just have a differential equation is just whenever we have dy dx equals whatever. Okay. So it's the derivative equals, and it gives us the equation of the derivative. It could have x and it could have y in it. But what we're going to do is solve them. This is introducing you to the indefinite integral where we don't have bounds there on our integral. So the big thing here, whenever I do find what y equals, as I do the antiderivative of whatever I have here, I'm going to get antiderivative plus c. That c is going to be really important here. And then what they'll usually do is give you an initial value, in other words, a point on the equation. You'll plug it in so that you can solve it for c. Did y'all do all that in the Khan Academy? Did you see all that? We call them initial value problems a lot of times because they'll give us an initial value for the function, which is actually just a point on the graph, and we'll use it to solve for c. So let me show you what I'm glad you asked what that would look like, because I'm going to show you what it would look like. Okay, I got that. For example, if I have dy dx equals secant squared x plus 2x plus 5. In this case, I want a general solution of what that looks like. I want to know, find all the functions for y. Tell me what y equals. What could y equal? Y. Let me just write this way. Secant squared x plus 2x plus 5 dx. Do you all agree with that? Because this is the derivative, so I'm kind of essentially doing this, right, to find it. So I have to think in terms of antiderivatives here. What is the antiderivative of secant squared? 10x. So I have tangent x. Those integral properties, let me split this up, right? You should, that's an easy one. Plus, what's the antiderivative of 2x? X squared. Yep. Antiderivative of 5. Am I done? Plus c. I got to include that plus c. Now, this one didn't give me an initial value. It didn't give me a point, so I can't solve for c, so I'd have to leave it there. Okay, but whatever, any constant I plug in would give me a function that would satisfy that.
You said not to write the c, though. Like
when you're indefinite, but this is an indefinite because there's no bounds there. You leave C. If you don't have a point, you definitely leave C. So this would say find a general solution, and so you leave the C in there. If it says exact and it gives you a point, they'll give you an initial value and tell you. We'll do one like that in just a second. But yes, bounds are definite, no bounds are indefinite. And indefinites always get that C at the end, unless you're giving an initial value. So nothing real new and strange here, right? Okay. Understand that this could be, if I write this, that is still a solution. It's not the only solution, but it's still a solution. I just want you to really understand that that C could be any constant in the world. It could be +1, it could be -8. Any constant you put there would be a solution for that equation. Y'all good? Okay, let's solve one then that they give us an initial condition, and we have to find that C value. It's called initial value. Let's say dy dx equals e to the x minus 6x squared. And I tell you that the graph passes through the point 1, 0. Find the exact solution for this one. So what y'all got? 2 minus e is your c. So y would be e to the x minus 2x cubed plus 2 minus e. Yes. The same thing. You got e minus 2. You got e minus 2 here, I'm assuming, but did you solve it for c? Did you move them to the other side? Yeah, so solve it for c when you. So this would be my exact solution. That is Diff EQ. They're not any, I mean, it's pretty easy. I'm going to do a couple from your homework with you that are a little bit harder, just because of the antiderivatives that you're finding. That's the only thing that makes them harder, but the process is not bad. Let's do a general solution first. Let's do number because it looks so much fun. Do what? That's exactly right. General solution, add the plus C. If it's not a general solution, if it's a particular or an exact solution, then you're going to solve it. No, those are just some examples in the book. But this one is from your homework. Y'all get ready to be big mad. Yeah. It's good that you recognized it right away. You might not know what it was, but right away you went, oh, it's one of those things. The what? Like the, do y'all still have your sheet? Colors were such an issue. Okay. So one of you, whenever you finally saw it on the sheet, said, oh, there it is. And there it is indeed. It's the inverse sign, right? Heck yeah. So we got inverse sign of x. Now this is the part where y'all are struggling just a little bit. So I'm going to make it x to the negative 1/2. And I'm going to go through my rules with exponent properties. I'm going to add 1, okay, which would be x to the positive 1/2, right? And then this goes in front and divides. But if I divide by a half, because there's already a 1, I multiply by the flip. So this becomes 2x to the 1/2, which is 2 square root x. And it's minus because of here. So I've got minus 2 root x. And of course the plus c on the end can't forget. That's it. That's the general solution. Yes, it's a lot less work. And slope fields. I'm gonna talk about slope fields in just a minute, but easy. Right. I left you the video on U substitution yesterday. And we'll talk extensively, I know, we'll talk extensively about U substitution when we get there, but this is kind of a precursor to U substitution. But if I want to find a general solution here, okay, you really have to think this one through. And my first thought on this is whenever I look here and I'm thinking about doing the integral, my first thought is this e to the something, because e to the something, the derivative and the integral is always e to that something, right? But I've got a chain rule situation here, right? So what could I let my f of x be, or my antiderivative be, so that whenever I took the derivative, I'd end up back with this? Look at this. What if I let y be e to the sine t? Of course, my plus c. If you then took the derivative of that, what is dy dt? Now chain rule it. Cosine t, right? Plus c. So that's the answer. So you had to think about when you saw this, the point that I'm getting to is you saw this and you went, how am I supposed to find the antiderivative of cosine t and e to the sine t? Because you can't split up because you're multiplying, right? But if you think about, if you look at the e portion, because e to the anything, the derivative and the integral is e to the anything, and think in terms of chain rule, that's really, and what they were trying to get you to do yesterday or Friday was I'm not even going to go there.
Wait. What's Conway's?
The blue.
But how though? What about the cosine?
Okay, so this says dy dt, right? I found y. So let's go backwards and check what I have. If you find the derivative of y, remember this is just another notation if I do the prime or if I do dy dt. What is the derivative of e to the sine t? Not plus. Multiplied by what? What's the derivative of a constant? 0. So you have to think backwards and forwards to make sure. One more like that, and then we'll move on to the exact. And a general solution. Yeah. Think about here, you have already taken the derivative. So what did you start with? Started with something, yes. Anybody get it? What'd you get? I was going to say don't get it. That's exactly right. Make sense? Okay, so we're chain ruling. You're getting derivatives and integrals mixed up. I was looking for the antiderivative. So now if you go through and derive that with the chain rule, 4 sine u. Right. But you have to determine which part of it came from being chain ruled. That's the challenge there. He was saying, should I just ignore the cosine u portion of it? Since that's, and said, well, you have to determine which portion is coming from the chain rule portion instead of just the original function portion. Yes.
Why didn't it change from sine u to negative?
Say that again. Okay, so when you do the derivative, remember I go from the outside in when I'm talking about chains. So it multiplies first, it does the exponent, and then I have to do the derivative of the inside for the chain. So the derivative of sine would be cosine. Did I answer your question? I did not, did I? Yes. Let me see if this helps you a little bit. If you struggle seeing this, give me a variable, any variable besides x. W. Let's say I told you that W was sine u. Okay, it doesn't matter. What would the derivative of W be? So do you agree that I could possibly rewrite, and actually I'm going to say dW du here instead of, just so I can stay consistent in my notation. Then do you agree that I could say dy du is equal to 4w cubed dw du? Agree? So now if I integrate on both sides, is it easier for you to see that this is actually w to the 4th here, right, plus c? What is w? W was sine u. This is a very basic u substitution type problem, and that's what the point was getting to there. You're doing u substitution, you're just doing it in your head. That did not help y'all, I can tell. Pretend I didn't say that. Okay, let's do an initial value, and then I want to talk about slope fields for just a second. You like the u substitution, or you like just like that problem? Well, we normally use u instead of w, but because u was in the initial problem. We'll get to some where you'll have to do u substitution because it'll be near impossible without it, but for right now. This is an initial value problem. Equals 5. Equals 0. Solve the initial value problem explicitly. Sounds kind of bad, doesn't it? That's a 5, yeah. See what you get. I missed y'all. I miss doing math. My husband is 40 years old today. 40. Y'all used to get so old. Not me, though. You don't think that's old? I'm glad you don't think so, that you're so young and you don't think so. But you're in comparison to what your parents, are you comparing me to your parents right now? Really? But you're the baby. My oldest isn't just a freshman. 24. 24 when I had Kenzie, and then 7 when I had Bobby. I got married young. I was 21 when we got married. I was still in college. They get through school and everything first. Okay.
I swear. Is it 2 secant squared?
You're gonna find some. Wait, is your place C there?
Remember that coefficient property? We can just pull it out front.
That's what I did.
Okay, well, let's see. All right, so first thing we need to do is find V equals. All right, so for secant x tangent x is secant x, right?
Yeah.
So secant t. Whoa, Nelly. What you mean? Not as a power, but because it's a coefficient, it can be out front. You're getting mixed up with, you're thinking power rule, but I'm not doing that right now. So if I have x to the third, right, I add 1, so I get x to the 4th, but then in front I divide by 4. Everybody get there with your C?
I got that. I got it. Oh, that's nice T, zero.
Did everybody get there with the C first before I plug in my initial value? That's just a separate example. I was just illustrating that's again separate. They were asking what do I do about that 4 in front, and I was saying remember that property, if it's coefficient, I can just stick it in front. All right, so let's plug in what we know. I know that 5 should equal 4 times the secant of 0 plus e to the 0 plus 3 times 0 squared. See why it's called initial condition? It's where we start, times 0. Secant of 0 is 1, so I have 4 times 1, 0, 0 plus c. Ah! Thank you, Allison. God, what's wrong with me? So my actual equation is just this without the C. It's always 0 something because it's an initial value, but the other value.
Oh, there's no more? Is there more?
All right, y'all ready for slope fields? Let's do it. Remember, when we find a derivative, what we are really finding is the slope of the tan line. That's exactly right. So we're going to use that thought process to go through and find the slope fields. What are y'all doing? Sticking juice in your pocket? Oh my gosh. What this means is that anywhere I go on my graph, I can find the slope of the point at, I can find the slope of the tan line at a particular point by using this equation, right? So if I went to the point 1, 2, right? The slope of the tan line at 1, 2 would be 1 plus 2 times 2, which is 5. That's a pretty steep slope, right? So what I would do, yeah, is that the way they did it on Khan Academy? So that's what we're going to do. I would start with the graph, and then if you want to do a table, I think you have to do, it looks like from -1, -1 to 1, and then up to 2. Well, then I should have done it like that. You will find a slope. So you're creating the slope field. So finding the slope itself is not enough. I have to graph those values. So for instance, at this point 1, 2, right? So at the point 1, 2, so right here, that's where I'm talking about. The slope is 5. So I would graph what's pretty close to, and I'm just going to be right here. It's a pretty steep slope. Just a little rendition of what a slope of 5 might look like, or close to. It doesn't have to be exact. If I come over to 0, 0, well, the slope at 0, 0 is 0. It's a horizontal line. That's exactly right. So I'd come here and do a little horizontal line. And so what you're going to do is you're going to find this slope at every point. We already found that one. At every point. So that's what it asks us to do. It asked us to construct a slope field for the differential equation using the lattice points shown on the graph. Yeah, so it's got these points mapped out. And so it's what you have to do is go to each of these points and go, okay, so we did 0, 0. What about 1, 0? The slope at 1, 0 is 1. So a slope of 1, it's not going to be nearly as steep as that, right? It's going to look something more like that. And the slope at -1, 0 would be -1. Right? Are y'all following me on that? And so I would go to every single No, if you can do them on your own, you don't have to. Right. Now, understand your derivative equation does not have to have x and y in it. It could just be, and this is number 29. And what that means is, it doesn't matter what your y value is. Your slope is your x value. So if I'm on this coordinate plane here and I'm graphing the slope field itself, well, at 0, 1, well, 0, 0, it's of course 0. At 0, 1, again, it's 0. At 0, 2, again, it's 0. Whenever I come over here to x is now 1, that means my slope is going to have the value of 1 for all of these. Because the y value is irrelevant. It doesn't matter. My y value is not impacting my slope. What's the slope value there? -1. -1. -1. -1. -1. -1. Okay, so let me ask you this. If that's the slope of the tan line of the curve, can you see what the curve itself might actually look like? Well, what's the antiderivative of x? If I solved this differential equation, right, y would equal what? 1/2 x squared. What's the c doing? Graphically, what does that c do? But what does it do to the function as it changes? Up or down, right? So do you see that I've really graphed the solutions, and I've graphed every possible solution? Because look, right? It's every parabola on here, just shifted up or down, but y equals x. It's the solution to the differential equation, is essentially what, and that's why we do it here with the Diff EQs. Does that make sense? Okay. I think I'll stop there. I think it's cool too. I like slope fields.